My name is Vladislav Padres, and today I want to tell you about curvature of a beam. When loads are applied to a beam, its longitudinal axis is deformed into a curve. As illustrated in Figure 1, the resulting strains and stresses in the beam are directly related to the curvature of the deflection curve. To illustrate the concept of the curvature, consider again a cantilever beam subject to a load P acting at the free end on the figure 2a. The deflection curve of this beam is shown in figure 2b. For purposes of analysis, we identify 2 points, M1 and M2. On the deflection curve, point M1 is selected and an arbitrary distance x from the y-axis, and point M2 is located a small distance derivative s further along the curve. At each of these points, we draw a line normal to the tangent to the deflection curve, that is normal to the curve itself. This normal intersect at point OH, which is the center of the curvature of the deflection curve. Because most beams have a very small deflection and nearly flat deflection curves, point OH is usually located much farther from the beam than it's indicated in the figure. The distance M1OH from the curve to the center of curvature is called the radius of curvature, Greek letter ρ, and the curvature, Greek letter kappa, is defined as the reciprocal of the radius of curvature. Thus, kappa is equal to 1 divided by ρ. Curvature is a measure of how sharply a beam is bent. If the blunt load on a beam is small, the beam will be nearly straight, the radius of curvature will be very large, and the curvature will be very small. If the load of increased the amount bending will increase, the radius of curvature will become smaller, and the curvature will become larger. From the geometry triangle OHM1 M2 in the figure, in the second B figure, we obtained the multiplication of ρ and derivative theta is equal to derivative s, in which derivative theta, measured in radians, is the infinitesimal angle between the normals, and derivative s is the infinitesimal distance along the curve between point M1 and M2. Combining equals first and equals second, we get kappa is equals to 1 divided by ρ is equals to derivative theta divided by derivative s. These equations for curvature is derived in textbooks on calculus and also for any curve, regardless of the amount of curvature. If the curvature is constant throughout the length of a curvature, the radius of curvature will also be constant, and the curvature will be in arc or a circle. The deflection of a beam are usually very small compared to its length. Consider, for instance, the deflections of the structure frame of an automobile or a beam in a building. Small deflections mean that the deflection curve is nearly flat. Consequently, the distance derivative s along the curve may be set equals to the horizontal project derivative x. Look at the figure 2b. Under the special conditions of a small deflection, the equations for the curves become kappa is equals to 1 divided by ρ is equals derivative theta divided by derivative x. Both of the curvature and the radius of curvature are functional of the distance x measured along the x-axis. It follows that the position OH of the center of curvature also depends upon the distance. The sign convention for curvature depends upon the orientation of coordinate axis. If the x-axis is positive to the right and the y-axis is positive upward, as shown in the third figure, then the curvature is positive when the beam is bent concave upward at the center of the curvature is above the beam. Conversely, the curvature is negative when the beam is bent concave downward and the center of curvature is below and the beam. So that's all about the curvature of a beam for today, and thank you for attention.